Okay, so we're going to move on to chapter 2. And in chapter 1, like most chapter 1s in every text, it kind of introduces what the heck is this topic, what's the history of it, what are we trying to do here, and then kind of briefly gives you, a little bit of sense of the material. And chapter 2 is where we really start to move into, solving these things. So we're still going to talk about linear programming models and constrained optimization models, but this chapter, we're going to learn how to solve them. We kind of skipped ahead a little bit last week when we used Excel Solver. We're going to do a little bit more of that today, okay? So, just to review, a linear model consists of the following components: a set of decision variables we know, an objective function, the thing that we're trying to maximize or minimize, and a set of constraints, the things we're holding back. So there's a lot of applications to this, and we talked about this in week 1. Marketing, how do you spend your advertising dollars to maximize impressions or maximize sales? Manufacturing, production mix models, how much of product A to make, product B to make, how to blend things together to make it, both rigid and efficient or whatever it might be. Finance, we'll talk about portfolio models. Everyone has a little bit different investment personality. How do we maximize your utility versus someone else's utility? Maximize your gain, limit your exposure. Agricultural examples are all there. So what's nice about linear programming, okay, is if we can set up a business problem to follow this, to have decision variables, objective functions, and constraints, there are some very, very efficient solution techniques. And I'm going to show you 2 tonight, okay? The first one we're going to do, and this is kind of crazy to say this, but we're going to do something called the graphical model. And we're not going to use the graphical model, okay? I'm going to show you the graphical model because it helps explain some concepts in chapter 3 more. It kind of helps you visualize what is happening here. The graphical model would be like, in the 60s and 70s, I'm sure if you took an MBA course, you had to use graph paper and you use this to figure out these models. But now today, we're going to use Excel Solver. But I'm still going to show you the graphical model, okay? So the importance of this is if a business model fits this, great, we have some solution techniques, and I'm going to show you those this evening. And what's also better is now that we use spreadsheets, not only can we get a solution, but we can do what-if analysis with that solution. So not only can we have our cake, but we can eat it too, right? We can say, this is our solution, but what if we did this? How could we make things better? How could we make our profit higher? What would we have to change? What would we have to tweak? What if this happened? So we can do a lot of what-if analysis and scenarios. Now, linear programming is somewhat limited, okay? Somewhat limited. And when we do linear programming, we have to assume that we adhere to these assumptions. Now, the problem is, in reality, we break a lot of these assumptions. Okay? In reality, we break a lot of these assumptions when we use linear programming. So you may be saying, well, then if we break these assumptions, we have to adhere to these assumptions, but we break them, why are we doing this? Well, you'll see a lot of times we're going to come up with a solution, and the solution is going to be saying, well, we made a lot of assumptions to get here, but this solution is valid, no matter what those assumptions were, even if we're violating those assumptions. We're going to do next week something called sensitivity analysis, which sounds like some kind of training you had to go to because you did some of the work. But it's not. It's after we solve this, okay, we're going to be able to see how sensitive it is to changes in various variables, okay? So let's just go over these assumptions now, and we'll come back to them next week. Assumptions of the linear programming model. First, the parameter values are known with certainty. So when we talk about parameter values, we're talking about like those coefficients. Like we said, like we're going to make $80 for every acre of corn and $60 for every acre of barley. And we're saying we know those things for certain. Well, when a farmer plants his field, does he know those things for certain? He doesn't know if there's going to be a great crop or a bad crop or there's going to be a drought in the middle. He doesn't know, right? He doesn't know. And oftentimes when we manufacture something, the same thing. We don't know that we're going to make, it's an estimate, we don't know we're going to make this much profit because we don't know what the economy is going to be like, we don't know what the demand is going to be like, but we still have to assume that we know those coefficients with certainty. But we violate that off. The second thing is that most, or the objective function and the constraints, the things that we model, exhibit something called constant returns to scale. So what that's saying is that, if item 1 costs me $5 to make, then item 1,000,000 also costs me $5 to make. But we know a lot of times that's not the case, right? A lot of times there's a marginal difference, right? Maybe the 1,000,000th item only costs you $1 to make, right? You've bought things in bulk. You understand that, yes? But we have to assume that it's constant because remember it says linear, right? And linear things are constant. Okay, so we have to violate that. We also say there are no interactions between the decision variables. And in reality, sometimes we violate that. Sometimes, if you make product A, it's better off making product B. There's some kind of synergy there, some kind of symbiosis. Maybe, it's not good to make this with that, but we have to assume there's no interactions. There's no relationships. And then finally, and this one's not as bad, the continuity assumption, variables can take on any value within a given feasible region. And sometimes we violate this, but it's not a big deal. If I say I'm going to make 89.35 pies, I'm trying to figure out how much my production should be at my bakery, and I say I'm going to make 89.35 pies. Well, I would never make 3/500ths of a pie, right? But pies are kind of negligible, so what if it's 89 or 90, right? It doesn't matter. So we violate this assumption, but usually it doesn't matter. Now, if I'm talking about how many stealth bombers I'm going to make, boy, that matters, right? Those things are not negligible. Yes, 89 and 90 is a big difference. Okay. So these are the assumptions that we have to adhere to, and we're going to solve these tonight. Now, what I'd like to do, and I'm not quite ready for a break yet, so what I'd like to do is we're going to do, and this is in your book, on page 51, and it gives a solution in 52 and 53, but I want you to go through, and we'll do that together in like 5 minutes, but right now what I'd like to do is read 50 and 51, and I'll try to project it, at least part of it. Yeah, I'll project it. And I want you to identify those 3 things. Okay, once again, I want you to identify the decision variables, the objective function, and the constraints that we have. Okay, identify those things. Once we have that identified, once we've gone from that word problem to the mathematical model, we're going to solve this thing 2 ways. We're going to solve it graphically. You're just going to observe that, understand some things about it. Then we're going to solve it with Excel solver. Okay, so take 5 minutes. I'll try to project it up here so you can see it. And then we'll come together and do it together, okay? And you can work. All right, I'm not going to read. You guys had the opportunity to read the case. I'm not going to read it to you. But here's the deal. This is what's called a classic production mix model. Okay, and we're going to do a lot of these at the beginning because they're very easy to conceptualize. And we are working for Galaxy Industries, and we are making 2 models here of these water guns, the Space Rays and the Zappers. Okay, and they're produced in lots of 1 each and made exclusively from a special plastic compound. We know that 2 of the limiting resources, so as soon as we hear that word limiting resources, we're thinking constraints, right? Are the 1,000 pounds of the special plastic, and we only have 40 hours of production available this week. We also know that we have our marketing department is concerned with our market, so they want us to limit total production to no more than 700 dozens. And they say, we don't want Space Rays from exceeding that of Zappers by more than 350 dozens. So it can exceed, but not by more than 350. We also have some input from our cost management department. They told us that we make about $8 per dozen for Space Rays, about $5 for Zappers. We know that what goes into those things, 2 pounds of plastic for every dozen Space Rays, 1 pound for every dozen Zappers, and production time of 3 and 4 minutes respectively for those items. So it looks like right now we go through an analysis, and I think It's the management has decided, and it looks like they make $4,100 per week, okay? I can't remember what the mix is, but they go through, someone said, let's do this, and they make $4,100 per week. And they've come to you as the expert to say, what would the optimal mix be? So first step is we want to set this up. We want to go from the model to the mathematical model. So let's think about it. What are our decision variables first? What are our decision variables? What are we deciding here? What can we decide? What can we decide?
How many to make?
Yeah, how many of each to make, right? So, and it's important that when we come up here, we make sure we get our units correctly. So x1 is number of dozens of space rays, right? So this came in dozens, right? We produce these in lots of, and dozens of zappers. So that's our x1 and x2. What are we trying to maximize or minimize here? What are we trying to maximize or minimize here? What is our objective? Obviously, most of the time it is to maximize profit. But we need our profit in terms of my decision variables. So I'm going to say max. How am I going to get from to a function, objective function? Well, I know on the table on page 51 says, I make $8 for every dozen space rays and $5 for every dozen zappers. So if I make one of each, that's $13. Two of each, that's $26, right? That's the equation for that. Subject to, such that, however you want to say it, we have some constraints going on. What are some, talked about limiting factors, okay, limiting factors. What are our limiting factors here? What were our limiting factors? Okay, one thing was plastic, yes? I think we only have 1,000 pounds of this plastic. So that is an upper bound constraint. We don't have to use it all, but we can't use more than 1,000 pounds. That's all we have. And I think it told us we use 2 pounds for every dozen space rays and 1 pound for every dozen zappers. So that was our plastic. What else do we have limited quantities of? Time. Very good. So I think it said we had 40 hours of production time. But then when it gave us our coefficients, it told us that space rays use 3 minutes per dozen, and zappers, I think, use 4. And we have 40 hours of production time. Now, there's an issue with that. What's the issue with that equation that I just wrote? What's the issue with that equation I just wrote? Every equation has to, the right-hand side has to match the left-hand side. The units it has to. I have minutes on the left-hand side and hours on the right-hand side, right? 3 minutes, 4 minutes, and 40 is terms of hours, right? So it's a mismatch. So there's 2 ways I can correct this. What is one way I can correct it? What can I do?
40.
Yeah, the easiest way is probably to say, well, since this is all in minutes, let's make this side by minutes, right? So 40 hours, 40 times 60, that gives me 2,400, right? Put it all in minutes. The other thing I could have done is put it all in hours. So I left 40 here. I divide that by 60, divide that by 60. I'd get 0.05 and 1/15. That's ugly, right? I don't want to deal with decimals. I like to deal with wholes. So that's the best way to go. Okay? That's like the physical constraints. If you will, those are the hard constraints. But marketing, those buggers in marketing, they gave us some constraints as well. We call these kind of constraints like discretionary, because it's not a physically limiting factor, but it's like contractual almost. Our marketing department said limit total production to 700 dozens, right? 700 dozens. So that would be x1 plus x2. The total production has to be less than or equal to 700. Okay. And finally, they said space rays cannot exceed zappers. Let's see how it's written. This is a tricky one. Where's it at?
About 350.
Yeah, let me read. To prevent weekly production of space rays from exceeding that of zappers by more than 350. So space rays is x1 and zappers is x2. So it says x1 has to be less than or x2 plus 350, because if we think about it, it can be more, it has to be less, but we can give this guy like 350 more. So the way we write this, we want to get only constants over here. So x1, to get rid of this x2, we subtract it from this side, and subtract it from this side, and we're left with x1 minus x2 is less than or equal to 350. So it's fine for this to be, if this were 200 and this were 100, it exceeds zappers, but only by 100. So 200 minus 100 is 100, I'm okay, right? But if this were 500 and this were 100, 500 minus 100 is 400, hey, I'm violating that constraint. So you see how that models that situation? That's not as intuitive as the others, but you'll get there as well. Okay. Also, we can't produce negative space rays or zappers. So x1, x2 greater than or equal to 0. How about the integer constraint? Would you use the integer constraint here? Oh, I forgot to record. I think I did. Would we use the integer constraint here?
Yeah.
I didn't forget. Why? You said yes. Why would you use it?
You know, it could produce half a space gun or whatever.
Okay. Well, think about what the units are in. So think about that again. The units are in what? What are the units in? Read the decision variables up there. Number of. So I can produce a half dozen, right? That's 6, right? Or a quarter dozen, that's 3, right? Even that, though, even if this were just in units, I probably wouldn't use the integer constraint. And the reason I wouldn't is, you'll see later, that limits us too much. And if the thing I'm using is negligible, like space rays and zappers, these are like, penny items. No big deal. So I'm not going to use the integer constraint. I only use the integer constraint when I really have to, like staffing models, or if I'm producing like how many buildings do I want to build, or how many homes do I want to build in this development. That has to be an integer, right? There's certain times, but it can't be something negligible like space rays and zappers. So thank you. Okay. All right. So that is our model. Okay, that is our model. What we're going to talk about tonight, and I used to do it on the board, but I'm not very good with this, is we're going to talk about how to solve it. So at 7 o'clock, we've been at it an hour. Let's take 10 minutes, come back, and we'll segue into solving it graphically, which you won't have to do, but I want you to pay attention to it. And then we'll spend the remainder of the class solving this one with Excel, and then we have a couple other ones I want you to solve with Excel. Okay? So take a 10-minute break, come back, and we'll start there. Okay, so this is the model, the mathematical model we came up with. And that's all we've done is we've taken this business situation and put it in terms of a mathematical model. Now we want to solve it, okay? The first way we're going to solve it is something called the graphical method. This is the one that I don't ask you to do this on the exam. You don't have to ever do it. I don't even ask you to do it on the homework anymore. But I want you to understand it, okay? So the first thing we do with the graphical method to solve this is we graph what's called the feasible region. Okay, the feasible region is all the points that are feasible, meaning all the points that do not violate any of these constraints, right? This defines what is possible, and by doing so, it defines what is not possible. So what we do first is we graph the feasible region, okay? So let's take these one at a time. The first one, it says, is this tells us then x1 and x2 have to be positive. So remember there's 4 quadrants, right? This is the only quadrant where x1 and x2 are both positive. So we're graphing x1 on the traditional x-axis and x2 on the traditional y-axis. So this is the number of space rays we make, and this is the number of zappers we make. So this only works well when we have 2 decision variables, right? Because we only have 2 dimensions on a graph here. Now, we want to layer in, okay, the plastic constraint. The plastic constraint is a line, is it not? It's a line. It says 2x plus 1 is less than or equal to 1,000. Now, how do I graph a line? There's 2 ways to graph a line. What's one way to graph a line? I can have a point and a slope, right? That defines a line. Or 2 points define a line, right? So let's do the plastic constraint. Let's say we make no x1s. What's the most, no x2s. What's the most x1s we can make? 2x1 is less than or equal to 1,000. What's the most space rays? We make no zappers. What's the most?
500.
Okay, 500. So the first point you see is 500 and 0, right? That's what this point is. We made 500 dozen space rays and no zappers. If we make no space rays, what's the most amount of zappers we can make? 1,000. So that's my second point. So then I draw a line, right, between those two that defines that line. Now what we're saying here is less than or equal to. So less than or equal to means that is now feasible and this is infeasible. All of these points violate that constraint. All of these points adhere to that constraint, right? So I have this graphed in, this graphed in. I would do that with these constraints. So the next one is, looks like it's graphing in my production time. So 3x1 plus 4x2 is less than or equal to 2,400. I could use the same thing. You know, if I make no space rays, the most zappers I can make is 600. There's that point there. If I make no zappers, the most space rays I can make is 800. There's that point there. Okay, I'm sorry, I reversed it. There's 600, there's 800. And it needs to be less than that. So what now becomes infeasible? Yeah, this now becomes infeasible because it's okay for the plastic, but it's not okay for the production time, right? So now I'm getting limited, more limited. Production, okay, the 700. Okay, what this is called is, we graph it in, we say x1 plus x2 is less than or equal to 700, but it's redundant because it hasn't changed our feasible region, right? If we eliminated it, we'd still have the same feasible region. And then we'll do the x1 minus x2 is less than or equal to 350, okay? So we graph that in. You don't have to do this, but I want to show you what's happening here. So all of the purple is not possible because it violates at least one of these constraints. All of the green are all of our possible solutions, right? These are all the things that are possible or feasible. Now I'm going to pick the best one. There's an infinite amount of points here. I want to pick the best one, right? I want to pick the one that maximizes my profit. So here's my profit, 8x1 plus 5x2. That's kind of the start of a line, right? That's kind of the start of a line because we don't really have a constant over here, but we can start out with like, I don't know, 2,000 and graph that in. And that's what we kind of do. I'm going to come back to this. So we'll say 8x is 2,000. And I graph that, it looks like here. Okay, that's 8x1 plus 5x2 is equal to 2,000. It looks like it's right here. Can I do better? Are there points that are higher with higher profit? Sure, right? And I keep pushing it out until I get to a point where, hey, if I push this thing out any further, it's not feasible, right? That last point it touches is my optimal profit. That point right there is my optimal profit. Does that make sense? Because 8x plus 1 plus 5x2 kind of defines that this line is going to have this slope, but we're not sure where it's going to be. So I'm trying to maximize profit, so I keep pushing it out, pushing it out, pushing it out, pushing it out, pushing it out. And the last point that it touches is right here. That's my maximum profit. Now, I'm going to go back here, and I think this might make more sense after we've seen that. There are three types, and this is good for a multiple choice question. There are three types of feasible points. And the first type is what's called interior points. Interior points are in the inside of the feasible region. And interior points are never an optimal solution. And it kind of makes sense when we think about we're maximizing or minimizing something. Things inside aren't extreme, right? They'll never be the last point it touches. So none of these things, all of these points, will never be the optimal solution. So we've eliminated an infinite amount of points. We still have an infinite amount of points that could be the solution, so it doesn't help us that much. Interior points will never be the optimal solution. The other types of points we have are boundary points. So all of these points on the boundary are called boundary points. And this one's a little tricky, but it says if there is an optimal solution, a boundary point may be an optimal solution. Okay, so just hold on to that a second. And the third type of points are extreme points. And extreme points are the corners, if you will. They are the corners of the feasible region. In this case, I have 1, 2, 3, 4, and 5. Okay? They're the corners of the feasible region. And what we say about extreme points is if there is an optimal solution, an extreme point will always be an optimal solution. So I've gone down from an infinite amount of solutions to 5 possible solutions. I know 0, 0 is not the solution, right? Because that's nothing, I make no profit. So the last point it touches, it's going to be a corner, right? It's going to be a corner, and it's going to be that corner, right? In this case, because of the slope of the line. If those coefficients changed a little bit, and let's say the slope of the line, I don't know, was more angled this way. I'm not sure if I'm going to be able to reach, but I kept pushing up, pushing up, pushing up, pushing up, pushing up. The last point it touched would be here, right? And that would be the optimal solution. Let's say it was angled this way, very sharp this way. Keep pushing it up, pushing it up, pushing it up. That may be the optimal solution, right? So interior points, never the optimal solution. Boundary points may be. Extreme points, if there is one, will always be. Now, when can a boundary point be an optimal solution? I said may be an optimal solution. When would a boundary point be an optimal solution? Like something here. When would that be an optimal solution? Something here. Man, can't keep that pointer straight. Too much caffeine there. When would a boundary point be an optimal solution?
When there are no extreme points?
Well, they're always going to be corners, right? You can't really have a round, because there's lines. They're all lines. So they're always going to be corners. But think about it. Let's say the profit line, the coefficients, it had a slope that was parallel to this line. If I keep pushing it out, pushing it out, pushing it out, pushing it out, well the profit line is going to overlap that. This equals that profit, this equals that profit. All of these points are an optimal solution. You guys know what I'm saying? What we have is multiple optimal solutions. If that equation is like exactly parallel to one of these, that profit line, hey, this is the solution. Yeah, but this is also the solution. This is also the solution. This is the solution. So that's why we say may be an optimal solution. If there is a profit line or the objective function is parallel to one of those constraints, hey, it might be right on a border, right? The last point it touches might be right on an edge, if you will. Not a corner, but an edge, okay? Now that was how the old school way, that we solve these. And why I show you this, okay? Why we show this in this class when, hey, we don't really use it anymore, is when we talk about sensitivity analysis next week, That's a difficult concept for a lot of people to get their minds around. And if we can think back to this example, it's going to help describe that, because in sensitivity analysis, we're going to say, what if something changes? How does that affect things? And if you say, well, if the constraint changes, hey, that changes the feasible region. If I make it bigger, well, I can push that profit line out further. If I make it smaller, well, the profit line's not going to go out as far. And if I change the objective function coefficients, hey, it might change the slope of the line. Does it matter or not, right? And it kind of helps to visualize those things. Now, the optimal solution is that point, and I'm not going to figure it out. We can solve for those two lines and see where they intersect. I'm not going to do that anymore. I can tell you, though, that point is 320 this way and 360 that way. Okay, it's 320x1 and 360x2. That gives me a profit, if I plug that in, that gives me a profit of 4,360. You remember what the manager was using? They were getting, I can't remember the production model they were using, but they were getting $4,100 profit. So we just increased profit by $260, which isn't a lot, but let's say it's $1 million. So we just produced, more than $260 million of profit by tweaking some things. Okay, so that's what we're trying to do here. Okay, that's what we're trying to do here. We adhere to all those constraints. This is basically talking about what I said. An extreme point is always an optimal solution. Okay, it's always going to hit one of those lines. And we could have multiple optimal solutions. Like if the profit line at the same slope as that line, all of these are optimal solutions. Okay. All right. So any questions on that? All right. So we did this. We started this last week, but we're going to finish it this week. We are going to solve this. That was one way to solve it. We got 320 and 360, old school. We're going to use Excel to do this new school. So I'd like you to get out. If you brought your laptop, great. If not, follow along with me. And we're going to go to Excel, and we're going to build this model from scratch. And I'm going to show you some functions that I didn't show you last week along the way. Okay, so I'm going to come up to, and this where I put things doesn't matter as much as what we reference, but for the first one, maybe follow along and use exactly what I do. In C1, we're just going to put our label space raise, and if it doesn't fit, just double click between the C and the D and it'll auto fit in there for you. And in D1, we're going to put the zappers. In C2 and D2, this is where my decision variables are going to live. The x1 and x2 are going to live here. So I'm going to start them off with 1 and 1. Okay, just start with 1 and 1. You don't have to put the borders on or anything. I'm going to skip a line. I'm going to write in B4, I'm going to write the word max, so I know what I'm doing with this. And it's just a label. And remember, I want to focus on coefficients. And that's why when I wrote it on the board, I tried to keep them in order because that's what we're going to do in Excel. We're going to keep x1s in column C and d's in column, and x2s in column D. We're going to focus on the coefficients. So for profit, the space rate coefficient was 8, and the zapper coefficient was 5. Right? 8x plus 8x1 plus 5x2. Now last week we did a formula. We said take C2 times C4 plus D2 times D4. Well, this week I'm going to show you a function in Excel that kind of does that for us. So put in the equal sign to tell Excel I'm using a formula, and write in sum product, all one word, SUM product. And I'm going to give it two ranges. I'm going to say C2 colon D2. That tells me the first range. Remember, the colon means through. So C2 through D2, comma, no spaces, don't use spaces in any formulas, C4 through D4, and then end parenthesis. And what sum product is doing, hence the name sum product, product means multiply, sum means add, it's multiplying this times this plus this times this. So if I had 10 things, maybe I had 10 decision variables, all I would have to do is make my range bigger. Like instead of C2 to D2, I would say C2 through K2. And instead of saying C4 through D4, I would say C4 through K4, right? So it's easier than going out through that whole function, right? Does that make sense? Now if I hit enter, just to make sure that this is working, it says 13. That's right, that's good. So let's just make sure if I change this 2 and 2, great, 26. And I'm just going to throw profit here so we know what that cell is. You can throw it above if you want, I don't care, wherever you want to put it. I'm going to go back to 1 and 1. I'm going to skip a line, and I'm going to go over a column 2. And I'm going to put subject to, or my ST, in A6. And in B6, I'm going to put these constraints in one at a time. And I'm going to say plastic. That's the first constraint I'm going to add. And once again, we want to focus on the coefficients. So for plastic, for space rays, it's a 2. For zappers, it's a 1. Now I realize I'm going to use that sum product formula over and over and over again here, right? So if I use it over and over and over again, what makes sense to do instead of typing it over and over again? Copying it down, right? Copying and pasting. Now, let's do it. I know this isn't going to work, but let's copy this. So I'm going to go up here to E4. I'm going to copy. I'm going to go to E6, and I'm going to paste. And I'm going to see, it's not right? It should be 3, and it's 21. Well, here's why, okay? What Excel does intuitively is it uses something called relative addressing. It says because you copied that formula down 2 rows, I'm going to copy everything or change everything in that formula down 2 rows. And that's what it did. It took C2, D2, C4, D4, and made it, copied everything down 2 rows. Well, I don't want it to do that, okay, because I always want to reference C2 and D2. So delete that, what we just copied in. The solution to for us, is to go back to the original formula. So I'm going to go back to E4, and I want to put it in edit mode. I can do that 2 ways. I can double click on it, and it puts it in edit mode. You see it goes in edit mode. Or I can go on that cell and hit the F2 function key, and it'll put it in edit mode. So whichever way you want to get there, put it in edit mode, okay?
which part of this formula do I want to change when I copy it, and what part do I want to remain the same when I copy it? So what do I want to keep the same, and what do I want to change when I copy it?
You want to anchor the C2, D2.
Very good.
Stay the same, and the rest you want to.
Very good. So C2 through D2 I want to anchor or make absolute, okay? So that no matter where I copy it, it stays C2, D2. The way I do that is I put dollar signs before the C and the D and the 2's as well, which is kind of a pain in the butt, but there's a toggle key that does that for me. So if I go in that formula and I just left click and highlight C2, D2, and if I use the F4 function key, which some of you may have to hit like a function key to get there, but if you have a big keyboard, it's just at the top. I hit the F4 function key, and it puts those dollar signs in for me, right? So it says, hey, you're using these dollar signs, I'll put them in there for you. If I hit it again, now it says, hey, the rows are static, the columns are not. Hit it again, now the columns are, the rows aren't. I'm gonna hit it again, they're all off. I hit it again, let's just leave it all static, okay? See, so I want the double dollar signs. And I hit enter. And it didn't change it, but now, when I copy this guy down, you'll see it left C2 and D2 alone, anchored, but it let C6 and D6 change appropriately. And now it's right. Okay? And we're going to say that this is the total plastic used is less than or equal to 1,000. And in F6, I just put less than or equal to. That's really just a label. And in G6, I put the constant 1,000. Let's add our time. Put in time. I'm going to focus on my coefficients. So we have 3 and 4. And now, all I have to do is either drag that down or copy it down, because it's already set up to keep C2 and D2 referenced. And that is less than or equal to 2,400. We want to add in our marketing constraints, so I'm just going to call this marketing 1. What's the coefficient? It's implied, but what's the coefficient for x1 and x2 there? Okay, so I'm going to put 1 and 1. I'm going to copy that formula down again. And that's less than or equal to 700. And then I'm going to put marketing 2, and my coefficients are 1 and what?
-1.
Very good. 1 and -1. And by now, Excel's figured out what I'm doing, and it has intuitively said, and maybe yours didn't, but it seems like sometimes they do. Mine intuitively figured out what I did, and it copied it down for me. So this is what you've done this every time, so I'm assuming you're going to do this again. Well, you've assumed correctly. So no need to do anything. And I'm going to say less than or equal to 350. Once again, I haven't solved anything. I have made it better than what's on the board, because now I can go up here, and if I wanted to, I could do trial and error. I could say, all right, what if I make 10 of each? You see how everything automatically changes? Well, I'm not making enough money. I got a lot of things left over. So maybe I set 100 and 100. know, still, well, I got a lot of things go over. Maybe I go to 400 and 400. And well, now I've got $1,500 profit, but looks like I'm blowing my marketing one constraint. I'm blowing my time, blowing my plastic, so that's too much, right? So I could do trial and error, right? And I could probably come close as a human, okay? I could look at this and say, yeah, what makes sense, what doesn't make sense. But I don't need to do that because I have something that will do trial and error much faster than I can do it. And it will zero in on the right value. So everyone have their Excel model working. So now we're going to invoke our good friend Solver. So if you remember, we turned that on last week. I'm going to go to Data. And the add-in we turned on is called Solver. If you weren't here last week and you want to turn that on, we need to go to File, Options, Add-ins. Whoops. File, Options, Add-ins, Go, and then we turned on the checkbox for Solver. And then you should have it under your Data tab. Now we need to invoke it, okay? And Solver needs to know about those three things. Same three things that we need to know about. It needs to know where they live. It starts with the objective function first. It says, all right, what one cell, and I can only put one cell here, what one cell represents what you're trying to maximize or minimize? What one cell represents what we're trying to maximize or minimize? What one cell? Jordan? E4. Very good. So I need to get E4 into that set objective. So I'm going to use a little spreadsheet. Click on E4, puts E4 in my dialog, then hit the pull down the window shade, and it puts E4 in there. I could just type in E4 as well. And it says, what are you trying to do with it? You're trying to maximize it or trying to minimize it? There are option buttons. So in this case, I'm trying to maximize that, right? Now the next thing it says is, all right, I'll make that big, but you have to tell me what I can change to make that big. I'll make that as big as I can, but you have to tell me what I can change. Well, what it can change is the same things I can decide on. It's my decision variables. Where my decision variables live. Where they live. C2 and D2, right? So I'm going to put that together as a range. I'm going to say, click on the little spreadsheet, left click and drag on C2, D2. This puts in here C2 colon D2. And hit the drop down. So I've told it about my objective function. I've also told it about what it can change. Now the one thing I haven't told it about is my constraints. If I solve it right now, the answer is going to be making an infinite amount of space rays, infinite amount of zappers, you'll make an infinite amount of money. That's not reality. So I need to tell it about things holding me back. So I can do this one at a time, and I'm going to do the first one at a time, and then I'm going to enter the last three in one step, and I'll show you how you do that. So let's enter our plastic constraint. I'm going to click over here on Add. And I'm going to say the total plastic I use, which is in E6, has to be, and I use this to say, is it less than or equal to or greater than or equal to? It's less than or equal to. It has to be less than or equal to what? And I could type in 1,000 here, but that's not good practice. So instead of typing in 1,000, I'm going to reference G6 and click Add. And it goes away. It looks like you deleted it, but you didn't. If I click Cancel now, it'll take me back to that original dialog, and you'll see it added in here E6 less than or equal to G6. Now what's nice about this model is all of these are going the same way. They're all less than or equal to. And I have them structured purposely so that my left-hand side is always in the E column and my right-hand side is always in the G column. So I'm going to add these three at once using a range. So I'm going to click Add, and on the left-hand side I'm going to say E7 through E9 has to be less than or equal to, I'm going to click in the right-hand side, G7 through G9 respectively. So that's actually adding three constraints. It's saying E7 is less than or equal to G7, E8 less than or equal to G8, and E9 less than or equal to G9. Yes?
You can do that right off the bat.
I could have done all four of those, yep. I just wanted to show you entering one and entering a range. What you can't do is, let's say right here you had a greater than or equal to in the middle of it. You know, you couldn't do that. You'd have to do the 2 and then the greater than, you know, you have to put them in the range. So you can structure it that way. You can put all your less than or equals together, or you can enter them one at a time. If you like that, that's fine as well. So I'm going to click Add. And then I'm going to click Cancel. Let's make sure I didn't screw anything up. It says maximize E4. Great, that's where my profit lives. C2, D2, that's where my decision variables are. E6 less than or equal to G6, fantastic. E7 through E9 less than or equal to G7 through G9, fantastic. By checking this box, make unconstrained variables non-negative, I'm adding in that last constraint. X1, X2 greater than or equal to 0. So that checkbox adds in that last constraint. Now the last thing it says is select a solving method. It's doing something behind the scenes, a solving method behind the scenes. We want to select simplex linear program for now. Okay, so just select simplex LP. Now the moment of truth. Okay, let's see if we can find our one best way. I'm going to click the button entitled Solve. If I did everything right, in this case it should say solver found a solution, all constraints and optimality conditions are satisfied, and it says, do you want to keep this solution? I'm going to click OK, let's keep this solution. And you'll see it arrived at the same thing that we arrived at when we watched the slides solve it mathematically. It says if you make 320 dozen space rays and 360 dozen zappers, you're going to make $4,360. That's the best you can make. We used all our plastic, we used all our time, and we adhered to our marketing constraints. It's all feasible, and it's the best solution. It is the optimal solution for what we're able to model here. Nice. It's the one best way. What's beautiful about doing it in Excel is now all these things are easy to change. If someone told me, you know what, we got an extra, I don't know, 1,200 pounds of or an extra 200 pounds of plastic. So now instead of having 1,000 pounds there, we have 1,200. Okay. Well, I put in 1,200 there. I click Solver. I click Solve. And it tells me, okay, now make 500 dozen and 200 dozen. My profit goes up to 5,000. I've used all my plastic. I still have some time left. I've used all my production, and I'm okay with the marketing to constraint. So I can do like what if analysis, which is nice. Did it work? All right. What I'd like you guys to do, we have some time left. It's only 10 till 8 at this point. I want you to try one from scratch before I let you go into the world with homework. So in Blackboard, under material by week, week 2, and and then click in Chapter 2, you'll see a document that says Chapter 2 Examples. If you click on that, it should open up a Word document. And I would like you to take a stab at number 1. It is a production mix, just like we did. So a couple things. One thing you might do, okay? You notice, hey, this is kind of similar to what we just did. We have 2 decision variables, we're maximizing profit. So what you can do, hey, you have a working model here, right, with all working formulas. Maybe right-click on that tab, click on Move or Copy, create a copy of it. So now you keep this one, and then let's say this one's example problem. And now instead of, you can do whichever way you like, start from scratch, or take that existing model and now change it from space rays and zappers to, looks like we're talking about, I don't know, type 1 and type 2 computers.
How did you copy that again?
2 ways I can do that. Okay, I can, right click on the tab and go to Move or Copy. And then by default it moves, so check the box that says Create a Copy, and it'll create a new tab for you with the same information in. The other thing you can do is if you hold down the Control key and then the left mouse button, you see how it turns into like a little spreadsheet with a plus, and then you can drag a copy of it wherever you like, and it'll insert it there. So whichever way you like. So go to it, and then we'll do it together. I think if you do it correctly, you should get, the answers at the bottom here. I think you should get, make 9 type 1s and 4 type 2s. Okay, so we have a production mix model. We want to determine the quantity of type 1 and type 2 computers to make, and we know we make $60 profit for a type 1 computer, $50 for a type 2. We also know that we have some time, production time. Looks like we didn't factor materials, but we know assembly time, inspection time. It takes 4 and 10 hours respectively, and 2 and 1 hours respectively. We need storage space, and they each take 3 cubic feet. And we know those things are limited. So I know those limited things are eventually going to end up in my constraints section, right? And they did. So if I write it on paper, that's what you should come up with. At least that's what I came up with. Is that what you guys came up with? Okay. So let's go to Excel and make it work there. What I would probably do with this, and you can do it from scratch if you like, but I'd probably take, hey, we have an existing model. Let's make that work. So this is a copy of an existing model that's working. So I'm going to change the labels. This will be type 1, and this will be type 2. And we're still talking about profit, but our coefficients are different. They're, what does that say, 60 and 50? 60 and 50 respectively. This first one isn't plastic, but I think it was production time.
Assembly time.
Assembly. I'm going to abbreviate that, I guess. An assembly is, what did that say, 4 and 10? And that has to be less than or equal to 100. I think the next one was inspection. God bless you. And that's 2 and 1. And that has to be less than or equal to 22. And this was storage. And it was 3 and 3. And had to be less than 39. The fourth constraint we don't need, right? So if we delete it, it will basically clear it out, but it'll probably still be in solver. We want to like obliterate it. We want to get rid of it altogether. So I'm going to delete this whole row. I'm going to right click on the 9. I'm not just going to clear the contents, I'm going to delete it. So I'm going to hit delete. Okay. And what's nice about that is if I just cleared the contents, it would still be in my solver, but I deleted it. So now when I go to solver, what's going to be, well, maybe not. Yeah, it did work. It now is set up exactly as we want it. It is maximizing E4, fantastic. That's what we want to do. By changing C2 to D2, fantastic. E6 less than or equal to G6, great. And E7 through E8 less than or equal to G7 through G8. If yours still has E9 and G9 here, you can click on it, go to change, and we can change it to E7, E8, G7, G8. Now if I solve, solver finds a solution. Ta-da. Make 9 type 1 computers and 4 type 2 computers. And we make $740. Now I realize, some of you are very familiar with Excel, and I know some of you are not familiar with Excel. So sometimes the struggle is just learning how to use Excel. So we're going to get out a little bit early today, and then anyone that is having trouble with Excel or just with this concept, I'll be here, and I'm more than happy to look over your shoulder and see what you're doing wrong or what we can work on and fix. For homework, there's going to be a whole lot of these, not a whole lot, I don't want to scare you, but there's going to be some of these for you to work on. So if I go to material by week, and then week 2, you would do these. This is on pages 101 through 110 of your course text. Do number 2, and do part A only of number 2. Number 3, Part A only. 7, 10, 17. And 17 has a typo. It says month in there, and it should be money. So it makes it hard to understand. Where you see month, it should state money. And number 28. All of these on Excel. Don't do these graphically. Set them up on paper, then put them in Excel and solve them. As I said, I don't collect homework. I don't check homework, but we review homework. So, if you're familiar with this, you understand it, and you only want to do 2 or 3, that's fine. Okay. The solutions are also going to be out there. So under Chapter 2 material, you'll see Chapter 2 Solutions Part 1. And if you want to check your work, you can click on that and see your solutions. If I can open that. Won't let me open up, but I assure you it's there. Okay. Any questions on anything we cover this evening? Okay, next week we're going to go into, well, actually we're going to stay in Chapter 2. There's a section of Chapter 2 we didn't cover called sensitivity analysis. If you want to read ahead, that's what you read ahead on. It deals with what we call like post hoc analysis, like analyzing after we have a solution, we do some what if analysis. Okay, so that's what we'll do next week. All right? All right. Well, have a good week. Drive safe. I don't know what the weather is like out there.